Exercise 3. In this one we have to justify those question marks that we left there in the proof of proposition 815. So let's recall the proposition, its statement roughly, and then its proof briefly, so that we can see where we had those question marks. So this proposition basically just said this: x is a subset of the set of natural numbers and x is infinite, then there exists a unique bijection f from n onto x that is increasing. Okay, so this was the statement, and the proof starts by defining a sequence recursively like this. A naught is defined to be the minimum of x, and an is defined to be the minimum of this set, the set of all elements x in x such that x is not equal to am for all natural numbers m less than n. In fact, we need not separately define a naught, it's included in this, but because in recursive definitions it's normally we first of all define a naught and then give another formula for defining the other terms, so that's why I am writing like this. And in fact, in the proof also we saw that this is the way we went through the proof. Then in the text it's mentioned that this set that is involved in this definition, this set, forget the minimum, just the set, is an infinite set for every natural number n. So that's what we now need to justify. So that is the first question mark. So in the solution we start off like this: for any natural number n, the set x minus this set. That means we are considering the complement of this set in x. For all m less than n is clearly this set. And this set is finite. Okay, so the set that we want to prove is infinite has its complement finite. Thus, since x itself is infinite, our set in question must be infinite. Is infinite. But why? This set is infinite. The justification is proposition 3614 part B. Okay, now let's look carefully. The complement of this set is finite. Now, if the original set is also finite, then the union of this complement and the original set, which is X, should be finite. And that's where we need this proposition, which says, this part B says, it says a number of things, but one of them is that if we take the union of two finite sets, then it is finite. But that union is X, which is given to be infinite, we would then have contradiction. So that is why this set cannot be finite, so it is infinite. That's how we have answered the first question mark. Okay, so now that we have the sequence defined for us recursively, the next thing is to notice this, that it is in fact a sequence of natural numbers. This is a sequence in N. A shorter way of saying the same thing, that this is a sequence of natural numbers, is to say that this is a sequence in N. This was another question mark. Why is it a sequence in N? And I think when we went through the proof in the text, that time itself I roughly explained why that is so. It's almost obvious, but still if one wants to prove it rigorously, then it can be done by induction. You just have to look at, first of all, the element A0, the first term of the sequence. It is by definition the minimum of X, and X itself is a subset of the set of natural numbers, so naturally this will belong to N. Then say you have supposed that AM belongs to N for all M less than N, for all natural numbers M less than N, where N is some arbitrary but fixed positive natural number. Then you want to prove that AN also belongs to N. By definition, AN is what? AN is the minimum of this set. Not equal to AM for all M less than N. Now, do you remember that after defining the sequence recursively, we also first of all made sure that the definition is a sound definition, that it makes sense. And in doing so, we proved that each such set is a non-empty set. Here, however, we are claiming something even stronger, that each such set that you see in the definition of the sequence, in the definition of each term, is in fact an infinite set. However, it is non-empty. But the point here is that this is again a non-empty and in fact an infinite subset of X, which itself is again a subset of N. So this minimum, which will belong to this set after all, is in fact again a natural number. So it's almost trivial that this is a sequence of natural numbers. In the text, however, it is there is a question mark. So we are just simply going to mention that it can be proved by induction like this. One can prove by induction and you can clearly see that this proof need not even be written. You can do it mentally. There is no twist. It's extremely straightforward. By induction that an is a sequence of natural numbers. Settling another question mark. Also, now we are going to address another question mark. So this part we have seen how it's true. Remember that other things were also claimed in the proof about this sequence, namely that the sequence is increasing which means that an is strictly less than an plus 1 for all n belonging to n. And one more thing that was claimed was this: an is not equal to am when the indices are distinct. Now this second claim is a consequence of this claim that an is increasing. How exactly this follows from this, that we already have. Not exactly that proof itself, but something similar. So let me first write what we are now going to do. Also, using the increasing nature of an, one can prove this second claim. But notice that we still have not shown that in fact this is increasing. We are coming to that later. Increasing nature of an, one can prove that an is not equal to am for any two distinct natural numbers n and m. And to see how, you go back to the solution of an exercise. See the solution to exercise 611 in the, this is the first problem of the first section of that chapter where we deal with sequences of real numbers. You see the solution, you will understand how this second claim of distinctness of the terms of the sequence follows from the increasing nature. Now we are going to prove that the sequence is actually increasing, but I need ink before that. Okay, we now prove that an is increasing, and this also we will prove by induction. So the first thing we need to prove is this: a0 is less than a1. Since a0 is equal to the minimum of x, a0 is less than or equal to x for all the elements of x. In particular, a0 is less than or equal to a1. Is a1 really an element of x? Let us see. What is a1 actually by definition? It is the minimum of this set such that x is not equal to am for all m less than 1. So that means this set is the set of all elements in x that are not equal to a naught, because for m we have only one choice, 0. In other words, this is nothing but the minimum of x minus a naught, this set, and this is a subset of x after all, and so its minimum, whatever it is, that's what we are calling a1, is after all inside x, inside the set x. So yes, because of this thing we do have a0 less than or equal to a1. But note one more thing, that since a1 is the minimum of this set and in this set we do not have a0, so a1 cannot be equal to a0. Note that since a1 belongs to this, and that is why this inequality will now become strict. a1 is not equal to a0, hence a0 is actually strictly less than a1. This is the basis for our induction. Now let am, say an, or okay, let us use strong induction. Don't really know whether we will need strong hypothesis or not, but let's just be safe and consider the strong hypothesis. am be less than am plus 1, for all m less than or equal to n. Okay, now what is it that we now need to prove? We now need to prove that a n plus 1 is less than a n plus 2, because if you take the largest value of m here n, then you get a n less than a n plus 1. The next thing that we need to prove is this. And because we are actually writing everything, let us also mention where n is some arbitrary but fixed natural number. Now you look at this containment. We are going to look at two sets. X is not equal to am for all m less than n plus 2. Okay, that is n plus 2 is a subset of the set of all elements x in x such that x is not equal to am for all m less than n plus 1. Is it true? To see that it's true, you just take an element here and see whether it belongs to this second set or not. So say we have taken one x. Now that x is not equal to am for all these values. That means x does not belong to a0, a1 and so on, a n plus 1. Okay, because x is not equal to such ai's. But then this implies x also does not belong to this subset. Naturally, if x is not in the larger set, it will automatically not be in the smaller subset also. But then that is precisely the condition that we have for the second set. So x must belong to this. So this set is in fact a subset of this. Hence, or we can continue this, which implies okay, now the important thing is, what does it imply? What does it tell us about an plus 1 and an plus 2? Note that an plus 1 is the minimum of this set by definition, and because this is a subset of this set, the minimum of this set will be less than or equal to all the elements of this subset. In fact, the minimum of this set is less than or equal to all the elements of this set. So in particular, it is less than or equal to all the elements of this subset, and this minimum is an plus 1. It is less than or equal to all the elements of this set and hence all the elements of this subset in particular. And one of the elements of this subset is an plus 2 itself, because that is the minimum of this set. So this is less than or equal to an plus 2. But since something like this will happen here also, since an plus 2 actually belongs to x minus this, because that's what we have here, in this that this condition translates into this. So an plus 2 cannot be equal to an plus 1. That's why that inequality will be strict. Thus, an plus 1 is strictly less than an plus 2. So, by induction, an is less than an plus 1 for all natural numbers in i.e. this is increasing. So we have settled this part also. Okay, so the claims about the sequence, that it's a sequence of natural numbers, it is an increasing sequence, its terms are all distinct, all those things now have justification. Now next, the proof of course proceeds. The proof doesn't stop here. The next thing we do in the proof is that we use an to define that function that we are seeking in the proposition. So we define the function like this. So that means whatever I am going to write here is not a part of the solution. The solution is going on and we have temporarily stopped here. F of n is defined to be equal to an. Okay. Now, this itself also raises another question. We have said that an is a sequence of natural numbers, but also, in fact, more than that, I think this is what we have in the textbook. I'm not sure if I have written it here correctly. I think in the textbook it is not claimed that an is a sequence of natural numbers, but rather an is actually a sequence all of whose terms are inside x. Maybe that is the claim. But if that is the claim, then that can also be proved by induction in that extremely straightforward manner. Why I suddenly realized this is because without that thing, this function would be meaningless if the an's are not in x. If some of them are not in x, then this function is meaningless, but they are, and that can be proved by induction again, just like how we proved that an is a sequence of natural numbers. Okay, so that part is there. And now, using this fact that an is not equal to am when n is not equal to m, one directly sees that f is 1 to 1. The next thing one proves in the text or in the actual proof is that f is onto, and in doing so, one of course starts by choosing an arbitrary element x in the range of this function, and one wants to show that this x is equal to some an for some natural number n. But the supposition is that, say that is not true, that x is not equal to an for all natural numbers n, then it automatically follows that x also does not belong to this set for all m less than n. X does not belong to this set for all natural numbers n right? Is that what we have? X does not, no, yeah, that's why I was a little confused. X belongs to this set. Why am I saying X does not belong to this set? Because X satisfies this condition for all the values of n. So in particular, for this finitely many values of n also, X satisfies that condition, so X belongs to this set. Now because X belongs to this set and the minimum of this set is by definition an, so an is less than or equal to X for all n. Okay, that's how the proof proceeds. X is an element in every such set, so X will be greater than or equal to the minimum of every such set naturally, and those minima are an. And then it is mentioned that since an is increasing, it is in fact greater than or equal to n for all n. Combining this and this, we then get that X is greater than or equal to n for all n. But X itself is after all a natural number, because we are choosing X from X, which is by definition an infinite subset of n. So in place of n, since these inequalities are true for all n, we can in particular choose n equal to x plus 1. Choosing that, you get x greater than or equal to x plus 1, and this is a contradiction. So this contradiction proves that our supposition that this is the case, that x is not equal to any an, is false, and that's why x has to be equal to some an, and that is why f is onto, proving that f is a bijection. But this part is a question mark. How does it follow from the increasing nature of n that an is greater than or equal to n? So this is the next thing we are now going to prove, and we prove this by induction. We next prove that an is greater than or equal to n this. So we start with the basis. Since a naught is after all a natural number, a naught is greater than or equal to 0, because 0 is the smallest natural number. So this is precisely what we want to prove when n is 0. Let, this is our induction hypothesis next, let an be greater than or equal to n for some arbitrary but fixed natural number n. Then an plus 1 is strictly greater than an. This is where we are using the increasing nature of our sequence an, and by induction hypothesis this is greater than or equal to n. So an plus 1 is strictly greater than n, which implies an plus 1 is greater than or equal to n plus 1. The strict inequality becomes an ordinary inequality if you add 1 to n. This implies an plus 1 is greater than or equal to n plus 1, and this itself also has a justification, of course, and we got this way back when we were developing the system of natural numbers itself. See proposition 2 to 12 part E. So that's just it. So by induction, an is greater than or equal to n for all n belonging to n. And so in the proof, how far have we progressed? We have shown that there exists a bijection from n into x, which is increasing, and the fact that f is increasing comes directly from the increasing nature of an. But then in the last leg of the proof, we need to prove that this f is unique, and that the proof of the uniqueness of f is also by contradiction. In the text, what we see is this. So what we do in the text is that, say, we consider that there is another such function g which is different from f, but which is a bijection and which is also increasing. It is different from f, but it has the properties of f. Then, because f and g are different functions, so this set will be a non-empty set. Because f and g will differ at least at one input, so the set of such inputs is this set. It's a non-empty subset of the set of natural numbers. So it will have a minimum m. Now, what does it mean for m to be the minimum of this set? Because m is the minimum of this set, m itself is also an element of this set. So, for that particular m, the f and g values will be different. But if we take values smaller than m, then there g and f will, they are identical. So, that means g of n is equal to f of n for all n less than this minimum, and g of m is not equal to f of n. But then the rest of the proof shows that in fact this condition would give us gm equal to f of m. That is a contradiction. But the question mark is that exactly how? Okay, so let's see how. We have g of m equal to minimum of because we are after all having g of m in x, okay, x minus g of 0, g of 1, g of m minus 1. The increasing nature of g coupled with the fact that just the increasing nature of g and the infinite nature of x, I mean the fact that x is infinite tells us that g of m has to be equal to the minimum of this. This part I am not going to explain exactly how this is true. Okay, so you have to convince yourself why and how this is true. Keep in mind that g is an increasing bijection from n into x. That is why we have this. But this is equal to the minimum of x minus, note that we have all these equalities. That means all these g values that you see here are in fact also the corresponding f values. X minus f of 0, f of 1, etc., f of m minus 1. But we actually know what the definition of f is. So this is the minimum of x minus f of 0 is a naught, f of 1 is a1, am minus 1. Or in other words, we can also write it like this: minimum of all x belonging to x such that x is not equal to an for all n less than m, because precisely that type of n we see here, all the natural numbers less than m, and this itself is by definition nothing but what? We have m here, so am, which is f of m, and proving that g of m is equal to f of m, which is a contradiction to what we were having there. So that is why our supposition that such a g exists having all the properties that f has, and but also at the same time being different from f, so no such g exists, proving that f is unique. And this is where the proof stops, and this is where our solution also stops, because we have completely justified all those places marked with a question mark. Let's see the next one. In this one, we have to prove proposition 818. Now, some hints are given in the text, but unfortunately those hints do not make sense. I don't know why. Maybe the author wanted to mean something, but there are some typographical mistakes, some obvious mistakes are there, and anyway we are not going to follow those hints in the solution. So let's just see what the solution is, and we need to of course recall the statement also. So this proposition says this. It is that proposition about which I remarked that the set y in the statement does not play any role other than the fact that it's the range of a function. Let y be a set and let f from n into y be a function. So that's just it. F is a function whose domain is the set of natural numbers and range is y, some set, some non-empty set of course. Then, and it's also not said that say f is 1 to 1 or something else. F is just a function. Then the image of the domain under the function, that is f of n, is at most countable. This is what we have to prove. So let us now see. The solution starts by defining another function like this. Define the function g from f of n into n as follows. Okay, so we are now going to define a function g from f of n into n. So let's not get confused. What type of set is f of n? F of n does not necessarily have numbers, because f of n, due to the nature of f, is a subset of y, and we don't really know what type of set y is. It's just some non-empty set. But whatever it is, we are now going to define a function g whose domain is f of n. That means the input values of g are going to come from y. The outputs, of course, are going to be natural numbers. And the definition is like this. For any y, in fact, to emphasize the fact that we are after all considering elements of y, so I am taking here y. For any y belonging to f of n, the set f inverse of y is a non-empty subset of the set of natural numbers, and hence has a minimum. Let me keep this statement here, because our solution is not going to be very long. Has a minimum. We define g of y to be equal to the minimum of f inverse of y. What do we see here? So the thing is that if we choose an element from f of n, y, then this element y is in y, fine, but y belongs to the image set of the function f. So the inverse image of y, which by definition is the set of those elements in n whose f images are equal to y, that set will be a non-empty subset of n. Why non-empty? Because we are choosing y from f of n. So there will be at least one natural number whose f image is y. So the set of all such natural numbers is this inverse image f inverse y. Now, being a non-empty subset of n, by the well ordering principle, this subset will have a smallest element, a minimum, and that minimum will be what? That minimum after all will be a natural number. That is our g of y by definition. So now for any y in f of n, we are getting a unique natural number here. So that is why clearly g is well defined. Now the thing we want to prove about g is that besides being just a function, g is in fact a one-to-one function, an injective function. To do that, we are going to take two distinct inputs for g and show that their outputs are also distinct. Let y and z be two distinct elements in f of n. Two distinct inputs for g. We need to prove that g of y and g of z are different natural numbers. Then watch this. F inverse of y and f inverse of z are disjoint. Their intersection is empty. Why is that so? That is because, you see, if you have some element in common, that is common to these two sets, say some element is there, say x belongs to this and also x belongs to this, then by definition of these inverse images, f of x would then be y for being in this set, but at the same time it will also be equal to z or z, giving us non-distinct y and z, which contradicts our choice. So that's why these two inverse images are empty, are disjoint. So g of y, which is the minimum of f inverse of y, will be not equal to the minimum of f inverse of z, that is g of z. Why? Because you see, the minimum of this set is after all an element in this set, whereas the minimum of this set is an element in this set. Because there is nothing common, so those two minima cannot possibly be equal. So that's why we have this distinctness. So distinct inputs have given us distinct outputs. Thus G is injective and this shows that the function, now g is the function from f of n into n. Now that range of g, if we replace n with the image of g itself, that is this. Into g of f of n is a bijection. The original g may or may not be on to n. That may not be the case. It may not be a function onto n, but it is definitely a one-to-one function of this onto its own image. And that is why the cardinalities of f of n and this will be the same, since, okay, now what is this? This is after all a subset of the set of natural numbers, because we replaced n with this set. Since this is a subset of n, this is at most countable. We already have this fact. And the result that justifies this is by corollary 816. So this is at most countable, and these two are in a bijection, so this should also be at most countable. That's what we want. So this is also at most countable, completing the proof and this solution also. Okay, so everything lies in the definition of that G. And let me end the video here itself. We are going to, of course, solve more from this set of exercises in the next real analysis update. And the next upload is on Tuesday, of course, since we have already gone through group theory from Herstein. So let us next again go back to field theory, field extensions. I think we are doing exercises. So see you on Tuesday with field theory. If you want to say something about these things, then please use the comment section below, or you can also mail me. The link will be there in the description. So see you on Tuesday with field theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.